Um, Welcome everyone to the 120th meeting of New Reference and Group Theory and Triangular Categories. Our speaker today is Lev Borisov from Rutgers, and the title of his talk is No Phantom Theorem for Certain Rational Surfaces. Or No Phantom Theorem for Certain Rational Surfaces. Yeah, please go ahead.
All right, so what I'm going to talk about today is joint work with Kimoi Kemboi. And it has something to do with this concept of a phantom. Before I talk about what phantoms are, let me just more generally talk about semi-orthogonal decompositions and more precisely semi-orthogonal decompositions in derived categories of coherent shapes on algebraic varieties. So my main object of interest will be GB of X, so bounded derived category of, say, smooth projective algebraic variety. And I will even say over complex numbers. I don't think anything really matters. Well, I don't think characteristic matters here all that much. I do probably care about it a little bit at some point, but anyway, complex numbers is hard enough. And if I have, so the semi-orthogonal decomposition is the following thing. I'm just gonna have two of them, and both of these are full, but moreover admissible triangulated subcategories. Of GB of X. And together they generate GB of X. And most importantly, there are no humps from B to A. What I mean is for any object in B and any object in A, no humps, humps from that object to the other object are zero. So no humps from right to left. The simplest example of such decomposition would be, let's see. Yeah, so it would be something like this. Let's say X is in P1. Then you can take two adjacent line bundles, let's say O and let's say O of -1. What I mean by it is not just O itself, but it's the subcategory generated by O. And that subcategory generated by O of -1. And together they generate the entire category. And there are no homes from O to O of -1. And no X either. All right. Let's see. I cannot scroll, but I can delete this, right? Yes. So the phantoms are the following things. So a full admissible subcategory of GB of X is called a phantom. I mean, more technical, it's a geometric phantom because it sits inside dB of x. If is well, I'll just say if it's Grothendieck K0, let's call this thing B. Is trivial. So maybe I should introduce some additional definitions. So a category is admissible if the inclusion has both left adjoint and the right adjoint. In the case of it being inside of dB of x, it's either one implies the other. And whenever you have a semi-orthogonal decomposition like this AB, it's more or less equivalent. I think it's actually the same thing as saying, yes? It's the same thing as saying that for every object f in dB of x, there's this natural distinguished triangle. So you have some kind of, let's call it f sub b, sorry. How do I undo it here? I'll undo it here. F sub b and into f sub a, where this is in b and this is in a. But anyway, so I started to sort of start talking about phantoms. There is, so the more technical definition of phantom is also that you have this K0 of B is 0, and also the Huxell cohomology is 0 of that category. But there is a statement, there's a theorem by, I think it's Kuznetsov and Gorchinsky, or just Gorchinsky, or maybe Orlov Gorchinsky, one of those, that says that in this geometric case, as long as you have K0 being 0, you also have the Huxell cohomology being 0. And therefore, you don't need that additional condition. And similarly, a quasi-phantom is just something a little bit weaker. So you have that K0 of B is finite. Yeah, so what's K0 of B? If you've seen like the Grothendieck group of abelian category, it's the same thing for triangulated categories. So you just take distinguished triangles, and for distinguished triangles, you write the relation plus minus plus, and you just mod out a free group generated by objects by these relations for all distinguished triangles. So it's really very much like the K0 in say category of coherent shifts, but it's just a group. Like there's no tensor product here or anything. Let's see. Is everything okay? Everybody can follow. Just want to make sure that. Okay. I mean, I don't hear anything. It's a little bit difficult.
I just wanted to make sure. So you said this is a theorem by Gorchinsky and Orlov?
I believe so. Let me take a look more precisely at what we quote. And let's see.
I was just wondering if it was this thing that you said was the theorem or something that you said before this. But anyway.
So let's see. So we are. So this is. Yeah. So it's Gorchinsky and Orlov, correct? Geometric phantom categories, 2013.
Okay. Thank you.
Yes. Yes. Right. So what is sort of the story? Like, why do people care about phantoms? Well, they're sort of started as an annoyance because you really wish that there weren't any phantoms. then you would be able to prove wonderful theorems. You can probably prove the irrationality of general cubic fourfold, all that good stuff. But unfortunately, that's not the case. There are, in fact, phantoms. But for a long time, it was really not clear how one would be able to construct them. So let me just tell you briefly how the first quasi-phantoms and first phantoms were constructed, just to give you the flavor of it. So I think first quasi-phantom of geometric origin, I think you can do some sort of, use some quivers or whatever, do something non-geometric. But first quasi-phantom of geometric origins, the ones we care about, I think, not sure who, but you can get it from Godot surface. So Godot surfaces are one of those surfaces with which have general type, and their Hodge numbers is something like this. And the fact that you have no hierarchical homology of the structure sheaf tells you that line bundles are exceptional objects. Exceptional meaning that their humps to each other is just C, and then there are no higher X between, from one object, from the object to itself. And you can construct, you can take specific 11 bundles, 11 line bundles, and they'll generate a category, let's call it A, and then what's left would be this quasi-phantom. So this is, here you have line bundles, and this is quasi-phantom. So it's pretty obscure, right? Like it seems that like those Godot surfaces, they are not the hardest to construct, they're not the easiest, but the surfaces of general type with very special Hodge numbers, fine. And this was just a quasi-phantom. I don't remember what the order of the K0 was, but not quite. But then there was another construction of an actual phantom, which was even worse. So let me erase this. Right. So now the actual first phantoms, or maybe I should say there were also quasi-phantoms that one could construct from fake projective planes, which is again not the most pleasant things to work with. Now there is another phantoms that were constructed in a similar manner, but from determinantal Barlow surfaces. And let me see, there was several authors. Yeah, so Bonning, Graf von Bottmer, Kasarkov, Sosna. And this was in about 2015. And again, it's a similar construction to the Godot surfaces, but more complicated surfaces. Again, you have a bunch of line bundles, and then what's left, the semi-orthogonal decomposition, what's left is a phantom. Now it's a true phantom. And I sort of had this feeling that phantoms are maybe something like that, related to some tricky surfaces of general type. But to my great surprise, in 2023, I guess, it was published in 24, Johannes Krah constructed phantoms on the most mild surface available, more or less. In 2023, on blowup of P2 at general 10 points in general position. Yeah, I mean, this was a complete surprise because all of a sudden you get this phantom on a pretty mild surface. And the argument wasn't even super complicated, but I mean, it was very clever. But somehow he started with a sequence of line bundles. I guess, okay, so 10, so 13 line bundles. So started with something for which there was no phantom, and then used this sort of non-geometric automorphism of the Picard lattice that gave him another collection of 13 line bundles. And then under the genericity assumption, so you have this A, which is generated by 13 line bundles, and what's left is a phantom. Which I don't know if what I kind of got out of this paper is we really know nothing about phantoms. I mean, not exactly nothing, but we don't really have a very good understanding of them. Now, why did Johannes Krah started working on these particular surfaces? Well, I don't know for sure, but it's possible that has something to do with the previous result of Piroshkov. So Dmitry Piroshkov, in his thesis, I think that was his PhD thesis, and he proved that there are no phantoms on Delpezzo surfaces. And I think he actually maybe proved it for blowups of 9 points. So that's not Delpezzo, but that's still okay. But I don't remember. And then Johannes Krah was trying to see if he could extend it, and he found that no, you cannot extend. And in fact, there is a very nice phantom there. So that's this is in Invenciones in 2024, that paper. So Kimoi and I were sort of looking at the paper of Piroshkov and Johannes Krah, and we were trying to see if we could use their techniques to do something. Our original approach, original thought was to try to maybe prove it that there are no phantoms on toric surfaces. That's a reasonable thing to do, and we still cannot do it. But somehow, as we were doing it, we were sort of trying to see where the techniques apply, and we did get a result. It's a 5-page paper. which I can now state that suppose you have a cubic curve in CP2, smooth cubic curve. Consider X, which is a blowup of CP2 at any number of points lying on this curve in very general position. What do I mean by very general position here? Well, for example, you can think about it this way. You take P1, P2, Pn, and you look at the corresponding elements in Pcar of P of E, and they have no linear dependencies. Meaning there are no, there is no way of writing something like this, right? So obviously you can always do it because you just, anytime you have, also, so you, for example, just make the coordinates to be, make the x coordinate to be transcendent of algebraically independent over the field of definition of your curve E, and that will do it. But I mean, it's probably true that you can get away with just general position. You may be able to see in the argument, but we did not try to push our technique as far as, which we tried, but we couldn't, and then we just said, okay, this is enough. We have a paper. Let's publish it, and then let's see if somebody decides to push it a little bit further. So let me maybe now explain the argument, and as I'm explaining the argument, you will see what where the difficulty lies. Okay, or any questions?
Yeah, sorry. You just mentioned earlier that when you started working on this paper, one motivation was looking at phantoms on toric surfaces, and you
Yes.
said that it is still an open question. I mean, am I
It's
correct in
still an
understanding
open
that?
question, yes. We don't know if you have a general toric surface. Are there any phantoms on it?
So would the hope be that your techniques could probably extend to the general toric surface? Yes.
Oh, I wish I could say that. No, I don't know. There is a big issue there that on a toric surface, there is an anti-canonical divisor, which is just the union of the boundary components. So it looks like a circle of P1s, and the difficulty is that this is reducible, and that's and you will see like there are certain statements just do not work there, and no, I don't think that, certainly immediately there is no way to extend it, and no, there are lots of things that are mysterious, like for example, are there phantoms on P3?
Right.
Nobody knows. I mean, it would be very silly to have a phantom on P3, but who knows? Maybe there is. I don't know.
And sorry, one last question,
Yes,
if you
yes,
just
absolutely. The more questions,
so
the
the
better.
so am I also correct in understanding that your methods can I mean can your methods okay am I correct in understanding that your work can't really recover Piroshkov's no phantom theorem, or can it?
We're using the same technique as Piroshkov's. Our result does not recover it, I don't think. because you know, okay, so if you have del pezzo endpoints, well, let's see, if you have, let's say 5 points, just for the sake of the discussion, can I draw an elliptic curve through those points? So these points are in very general position. Maybe, but it's sort of silly because we're heavily using Piroshko's machinery. So it's not like we're improving on his method. We're just applying his method.
Okay.
Yeah. All right. So let me erase this. Right. So let's see. So here's how the argument goes. And as I'm explaining the argument, yeah, so you'll see where the difficulty lies in trying to push it further. So what's special about this X? This is the blowup of P2. Is on this X, there is the anti-canonical divisor, which I'll still call E. It's a proper pre-image of E here, right? And there are all these other things. But the important thing for me is that you have this anti-canonical divisor. And it's smooth. And moreover, the very general condition tells me that if I look at the map from Picard of X to Picard of E, just the pullback map is injective. And then we say that there are no phantoms on such surface. Okay, now how does it go? Suppose there is a phantom. Then by the work of Nick Addington, any kind of semi-orthogonal decomposition of the ambient X induces an autoequivalence on the derived category of E as follows. So for any object, let's call it F in dB of E. Let's say I need a notation. So E inside X would be given by J. The inclusion is J. What you can do this. You can do J lower star F. Then you can do you can map it to B, to the category B. Let's see, what's our notation? Anyway, I'll just say this. So you'll take this, you'll take its B component, you pull the result back to E. This will naturally have a map back to F. And you will get a cone with the third object being some kind of T of F, where this is some autoequivalence of dB of E. So if E is not smooth, it still works, but it would be autoequivalence of the category of perfect shapes on E. This is true for any anti-canonical divisor. And it's miraculous. I mean, I don't know how he came up with it. And this is what is a big ingredient in Piroshkov's approach. It's a relatively short argument, but I'm not going to be able to reproduce it now. And it's about, it's in 2016 or something. So it's pretty peculiar. So I wish I could do it, for example, if it wasn't a divisor, but maybe complete intersection. So something of dimension 2, but I don't know how to do it. All right. I'm just going to take it for granted. I'm not going to say anything more. But now what we do with it is the following. Let's say I pick a point P in the curve E. Then I take O sub P. I take it push forward. I take the B component of it. I pull it back up. And I have this map to O sub P to, let's give it a name. Let's call it C sub P. I think this is what we call it. Yeah, we call it C sub P. And we have this. Now, because B is phantom, it means that this J lower star of O sub P, B is trivial in K-theory, has trivial K-theory class. And therefore, the same is true for the pullback. And it's just pullback to a divisor. So definitely also has trivial K-theory class. So now this still gives us a lot of information about this CP. So it's C of OP for some autoequivalence. And it has the same K-theory class as a structure sheaf of some point on E. And there are not a lot of objects in the category of elliptic curve that are like that. For example, you have this property hom from OP to itself is just isomorphic to C. And that tells you that the same thing is going to be now true for CP. It tells you that CP has to be just a sheaf. It cannot be something more complicated. What we're helped here is by the fact that the category of coherent sheaves on elliptic curve is hereditary. Because you're in a smooth dimension 1 case, every element of derived category is quasi-isomorphic to just a direct sum of the corresponding cohomology sheaves. And so everything, so and then what happens if you have more than one direct summand there, then you're going to have endomorphisms, which are not just multiples of identity. So it tells you that CP is just a sheaf. And then it has the same K-theory class as a point, so it means the rank has to be 0. So CP is, well, it's a sheaf with a cohomological twist. So this tells me that CP actually has to be structure sheaf of some point twisted by some even integer. questions? Because this is somehow the key step. And this is what breaks down like for toric surfaces, for example. Because you just your category of coherent shifts on this called Kadara cycle, on the cycle of lines, is not hereditary. You have a problem there. So you just don't know. There are in fact objects there that that have this the same K0 class as a shift of a point, but are not. So somehow the auto equivalences of elliptic curves, of smooth elliptic curves, are just much easier than auto equivalences of something singular. And any questions?
Just so you're using the triviality of the K theory class, but I mean, is that the only consequence of phantomness that is being used here?
That's the only consequence of phantomness that's being used, but that's kind of almost the definition of phantomness, right?
Yeah,
Like,
yeah,
it's
yeah.
not much. I mean, yeah. So I mean, like, more or less, what else can you use? Yeah. And I think this is more or less similar to what Piroshkov's doing as well. But okay, we can do better. So let me erase this and kind of reproduce it a little bit. So you have this J from E to X. I have this P in E, and I'm looking at pullback of the B component of the push forward of P. And then this maps to OP. And now this maps to this OQ of 2M. Okay. Next, we're using the following interesting object. We're looking at support of this J lower star OP B. So what this is, it's is a closed subvariety of X, and it contains P. The definition is this is a union of supports of the cohomology shifts of this object, So it contains P, but what we can say about it is we can argue that for very general P, it must be just P. So let me explain why. So if you take a hom from let's see, how does it work? Yeah, from this one to some kind of O sub R, so where R is a point in E, J lower star of O sub R. Then by adjunction, this is the same as a hom from J upper star, J lower star OP B to OR. And if R is not P or Q, then this is going to be 0. right? Oh, let's see, just a second. Q not equal P is. No, I forgot something very important. Sorry. I take it back. Q has to be P. Q must be equal to P because the K group of the elliptic curve is complicated, right? So different points will not have the same class in the K group of the elliptic curve. So actually, sorry, this has to be P. And then what happens is for R not equal P, you're not in there, so the support intersect E must sit inside P. But then if it's just a curve, here's my situation. I have a point P and I have this support. And the support intersects my elliptic curve only at the point P. For generic points on your elliptic curve, you're not going to have this property because there are only countably many points whose multiple is a restriction of any kind of class from the pcar of x, because pcar of x is countable. We're on a rational surface, and so for very general P, this picture is not possible. Then support of P, support of this J lower star also PB component is just P, and then Piroshkov has a nice little lemma that says that for phantoms, this implies that this just must be zero. You cannot have an object in your phantom category with a point support, because somehow from there you can argue that there is a you will have an element in there with non-trivial K group. I think just the structure shift of that point will be in B, and that's a problem. Okay, so what have we shown so far? Right. What we have shown so far is the following. This is my E, this is my X, and I proved that for very general P, this push forward of O sub P and its beta component is zero, B component is zero. In other words, this sits in A. In the other part of the semi-orthogonal decomposition with the phantom. This also tells me that for very general P, in my sequence, I had this J upper star, J lower star OPB, to O sub P, to this CP, which was OP of 2A, 2M, cohomological shift. Then this, because this is zero, it tells me that this 2M must be zero. So you just have O sub P to O sub P of zero, identity here, and okay. And then this is zero. Now, from here, by semi-continuity, essentially, that the same thing works for any, so this T, or the T was this autoequivalence of the dB of E. So T of P is OP now for all P. not just for very general P, but for all P. And that implies that T is just a twist. It's a twist by a line bundle. And then it's not too hard. Let's see, how much time do I still have?
I mean, you should get a full hour for the talks. I think we started at 5 past, so maybe you have 14 minutes.
Okay. Yeah, I won't need that much. Yes. So it's tensor by a line bundle, and then we say, okay, let's do the same thing, but not for a structure shift of a point, but let's just do it for the entire structure shift of E. And then we're gonna have this OE, and then it's gonna be OE. Well, it's gonna be L. But then it's the same story because this is a k-trivial. This is k-trivial, and this implies that L must be trivial. And then it's not hard to see that this T just has to be identity. Because there's essentially nothing else that you could go from OE to OE. So anyway, T becomes identity, and then this tells me that this J lower star OP of B is 0 for all P in E. Okay. So let me summarize where we are so far. So we're in a situation where, again, E and X, and if I pick any point here, then the push forward, basically that point, structure shift of that point on X lies in the A. Remember, we have this A, B being D of X, and this B is phantom. So this is our situation. And eventually, we want to show that phantom is just 0. But in the process, so far, we're saying, okay, structure shifts of those points lie in A. Now, the next step is just to argue the structure shift of other points in X lie in A. So now suppose I pick a point here, somewhere else, and I have a structure shift of OX. Then structure shift of OX, it fits into this distinguished triangle. And then what happens is yeah, so you see this one is in B. This tells me that for every point in E, the harms from OXB to J lower star of P are 0, because there are no harms from B to A, right? This lies in A, this lies in B, there are no harms. And from here, you can essentially from basic properties of the support, you'll see that the support of OX of B is disjoint from E. And this is the only place now where we use our assumption of being in very general position. By assumption on points being in very general position, or it's equivalent, well, not equivalent, but it's the fact that the the map from pkr of x to pkr of E is injective. The support always must contain X and is disjoint from E, but there are no curves on X which do not intersect E. So suppose of this, or XB must be just X itself. And again, by Piroshkov's, for a phantom category, this is impossible. So now I see that the J lower star, not J lower star, it's just OX. So OX is in A for all X. And that's basically it. If you have a semi-orthogonal decomposition and one of them contains structure shifts of all points, the other one just has to be zero. Like there's no, because you're not going to be able to find objects which don't map to any points. So this means that B is zero. And that's it. That's the argument. So we essentially were using the technology that was already there, but we had to use all of our assumptions. And the question is, and somehow, it's a short paper. It's a 5-page paper, but I think it's a nice observation. Somehow this existence of anti-canonical divisor is what you don't have in Johannes Krau's example, because he is blowing up 10 points on P2 in very general positions. So you kill off all the anti-canonical divisors. There are no cubic curves passing through those 10 points. I mean, he needs more than that. He needs some additional genericity assumptions, but still, we formulate a conjecture that you shouldn't have a phantom on a surface that has an anti-canonical, non-trivial anti-canonical divisor, but it's wishful thinking. We have no way of proving it right now. So maybe let's see if there are any questions, and after this, I'll say where one can go from here. Like, what are the open questions? Questions?
I have a question, but I don't want to ask it now. I'll ask it after we have stated your open questions.
Okay, I'll state my open questions then. Okay, let's see. Let me erase this. Okay. Right. So open questions. So the first one is drop the genericity assumption. So what I mean by it now, let's just take P2, take any endpoints on an elliptic curve, on a smooth elliptic curve, blow them up, get X. Yeah, you have something like this. And then prove that X has no phantoms. I feel like this might be doable, like, because everything works except the very last step. So I don't know. I mean, so this seems doable. We couldn't do it, but I wouldn't be surprised if Piroshkov like looks at it and says, yeah, this, and it's done in one page, right? So it's not. It's possible. But so I feel that we got stuck at the very last step, because what happens, you might have a point here which might have some kind of support of the corresponding object there would be this. It really feels very weird to have a phantom category whose objects are supported on just some curves, but we don't have a proof. But again, this would be like the lowest hanging fruit somehow. So I mean, part of it why we didn't pursue it is because, well, maybe it's not really that interesting, but okay, maybe it's interesting. Now the second, which is harder, we don't know how to do, is what if the curve is not smooth? What if the anti-canonical divisor is not smooth? Actually, if it was like a one nodal curve, I think there is hope because there is some decent classification, decent understanding of derived category of that curve, but it's still hard. But for example, in the case of the toric surface, this is my E now. This is my X. And we're stuck. The place where we're stuck is the following. So you have this sort of early on, we're stuck early, unfortunately. So you have this GL over star OP and B and this and OP, and then this is CP, which is some kind of autoequivalence TFOP. And they're in the same K class. And then so what? Somehow there are lots of autoequivalences. It's actually a very well-researched subject. Autoequivalences of this called Kodaira cycle. And there are some kind of topological characterization of these autoequivalences, but they're tricky. So it's not obvious for us how you could take something like this and say, well, this has to be this CP. So maybe there's a way, but we don't know it. But the biggest prize, I think, and this would be something great if someone could do it, is P3. Can one push this to higher dimensions? And I would be shocked if there are phantoms on P3. But again, maybe we just know nothing about them. It's also possible that there are. So what happens there is now you do the same thing, or you can, at least the same approach would be to take a case-free surface. Now let's call it S. And then you're gonna have this autoequivalence from dB of S to itself, which is identity on the level of K-theory. But it's harder to work with surfaces because for surfaces, you don't have the category is not hereditary. So you can't really say, oh, it has to be from a Schiff has to go to a Schiff or anything like that. And it's a generally open problem understanding autoequivalences of K3 surface, even in the simplest case where you have a very general quartic. So I think it's just unknown, and we looked for references, and there are lots of statements about what kind of autoequivalences you can get. So basically, you can get, sort of the K So there is a map from the equivalences to the just automorphisms of the K group, and the image you can say something about, but the kernel, it hopefully is, well, it's not zero. You can do just you can do just just do homological shifts, but it's not clear that there's that's the only thing. But this is where the difficulty lies. So I would really love for someone to tell me that, oh, for generic case resurface of Picard rank 1 of degree 4, there are no, this is all the autoequivalences, blah blah blah. I mean, the spherical twist and whatever, but it's not known, and I'm sure if it was known, probably Piroshkov would have done it, but because it's basically up his alley. But it's just much harder. Tricks are needed, and I think I stop here.
Thank you very much. Let us all unmute ourselves and give the speaker a round of applause. Okay, if you have any questions, you can ask them now. And the question that I had in mind was literally what you said in your P3 point.
Okay.
Because they previously mentioned P3, and I was wondering whether you would come back to it.
No. I mean, I'm, because the key theory is four-dimensional, right? So on P3, right? And it's just, it's just 4 dimensions, like it's Z4, right? So what, how bad can it be? Can you construct something, like 4 exceptional objects? And I don't know. It seems ridiculous that the P3 would have a phantom. But at the same time, I don't have any argument against it. And you see, there's a lot of flexibility here because S can be pick anything, any smooth surface. So not only, so I was thinking that you have this autoequivalences, right? But it has to be varying. You can imagine it varying as S is varying. So you're not going to be able to get away with just some kind of random autoequivalence on some random surface. It has to be really some kind of, so maybe the fact that you would have to have it, this autoequivalence uniformly for a whole family of K3s, that seems very unlikely that you would get something that's not just a homological shift. But I don't know a proof.
And when you made that comment about autoequivalences for general case resurfaces, and you said if this was known, Piroshkov would have mentioned it in his paper, I would have thought, of course, this is wrong, but I would have thought that if this would have been in some paper of, I don't know, Sasha Kuznetsov and Schindler and those people, but I'm sure that is not the case.
I have, no, don't be sure. My weak spot is always understanding the literature, especially this is, not, yeah, but, even in the areas that I'm supposed to be an expert, and this isn't one of them, my grasp of literature is always very tenuous. So, no, but I think maybe I did ask, but I looked at various, yeah, because I mean, I was actually thinking that maybe Huybrechts would have something in his book, because he talks about all the autoequivalence of the case resurfaces, and it's unclear. Yes, somehow. Yeah, no, it's somehow it feels silly, like what could it be? But it's just hard to construct. So how to say, like, what could be the point, like objects, for example, on the case resurface?
Yeah.
Maybe, I mean, I should talk to people like maybe, Macri, or some bridge stability people, right? Because they like their case resurfaces.
Yeah.
maybe they can say something, because I think all the sort of equivalence of K3 surfaces, they do come from some sort of Brisman stability stuff, and but I don't know. I mean, it's just this hereditary thing was really, really useful. We could immediately say that the autoequivalence would have to send a structure sheaf of point to a sheaf. And then on the elliptic curve, you can say, okay, that sheaf has to be torsion, either just a point or torsion free. And torsion free, there is just this indecomposable vector bundles that everybody understands, and then blah 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 it all. And then the rank just gets you. But for case 3, who knows? Maybe there are some objects which are just whose case theory is very simple, but they're not. It's not just the direct sum of their cohomology.
Yeah.
Like, that's the trouble.
Any other questions or comments? Okay, we got some people after you started. That was good. If we don't have any more questions for our speaker, let's thank Lev Borisov once again. Thank you very much for the talk. And because of the length of the paper, I really liked the speed with which you progressed today. I mean, it was very followable and it was very well done.
It had to be slower, because otherwise I'd run out of of the material in 20 minutes.
That was true. Thank you very much. Can you send the notes to me afterwards?
Oh, I don't have notes.
No. What you wrote.
I mean,
No, what you wrote on the screen. Actually, it's okay. It will be in the video.
Oh, I don't have it. I don't know how to do it.
It's okay. It's okay. It will be in the video.
Maybe it's just recorded, I guess.
Yeah. No problem.
Yeah.
Thank you. Thank you all.
Yes, thank you very much.
Thank you. Bye-bye.
Bye.